Last class we talked about the magnetic forces on currents, electrical currents, or charges, moving charges in magnetic fields. But I haven't told you, we haven't discussed how a magnetic field is created, how a magnetic field is manufactured. So today's class is about how electrical currents or moving charges actually create the magnetic fields that electrical currents or moving charges also experience. So magnetic fields actually convey magnetic forces between moving charges or between moving currents, like electrical forces conveyed, electrical fields conveyed electric forces between charges. So specifically, today I'm going to focus on these three topics with a brief introduction. The first topic is going to be the magnetic field of a straight wire, and we're going to explore that field, map out that field, discuss that field. Then we're going to talk about the magnetic field of a current-carrying loop. We're going to explore that. We're going to map that out and discuss that. And then finally, we're going to talk about the magnetic field of what we call a solenoid. I'll explain what a solenoid is, and we're going to map out and explore that magnetic field. So most of this class is about these three topics. I'm going to start with just an introduction about the fact, the discovery, that it's electrical currents or moving charges that make magnetic fields. Okay, so that fact that an electrical current generates around it a magnetic field, or that a moving charge generates around it a magnetic field, was discovered by Hans Ørsted, who was a Dutch physicist, and it was discovered kind of just accidentally. It was just an accidental discovery. He wasn't looking for currents to make magnetic fields. He accidentally found that currents generate magnetic fields. And he found that currents generate magnetic fields by observing the fact that when he switched on an electrical current, he noticed that compass needles in the neighborhood of the electrical current, so nearby the electrical current, were deflected, were moved. And so he realized the importance of that what he was seeing for the first time, observing, recognizing for the first time, was that those electrical currents were producing magnetic fields. So that was a big moment. It kind of unleashed a lot of work on quantifying the fields that are made by currents, the magnetic fields that are made by electrical currents. You remember Coulomb's law from electricity. You remember Gauss's law from electricity, which are ways of describing exactly how the force in the field works. Ørsted's work led to what's called Ampere's force law and Ampere's second law called Ampere's circuital law, which are kind of equivalents of Coulomb's law and Gauss's law in describing how magnetic fields work. So I wanted to show you first in a couple of slides just two ways that you can really see, picture, visualize magnetic fields from electrical currents. One of them is here. So one way, which is Ørsted's way, which is using compass needles. So here's a current-carrying wire, and the current is flowing from the bottom of the screen towards the top of the screen. And surrounding that current-carrying wire are some compasses, and they're compass needles. And these needles, compass needles, are deflected by the magnetic field surrounding the wire. They line up with the magnetic field surrounding the wire. And they actually showed Amsted and Ampere and other scientists that the field lines around a wire, the magnetic field lines around the wire, form concentric loops. And so you see here these compass needles mapping out that concentric loop around a wire. Nearby the wire, they discovered that the field is strong, so the compass needles are strongly influenced by the current in the wire. Far from the wire, the field is much weaker, so the compass needles are only weakly influenced by the wire. So this is one way that you can see a magnetic field with compass needles. The other way you can see a magnetic field is with iron filings. So again, here on the left-hand side, this is a current-carrying wire. So current is streaming up from the bottom of the slide to the top of the slide in this wire. Surrounding the wire, now not compass needles, but are iron filings. And they, too, allow us to map out, to visualize, to see the magnetic field. So they, like the compass needles, they align with the magnetic field, and they also move from regions of lower magnetic field to higher magnetic field. So they tend to cluster around the wire. In this picture here, you can see the kind of the spirals or the circles of iron filings that are mapping out the field. And as you get further from the wire, the circles become less clear. As you get close to the wire, the circles become very clear. That's because the influence of the wire is much stronger near the wire. The influence of the wire is much weaker far from the wire. So the iron filings also map out the field. Okay, so I want to talk about this long, straight current-carrying wire, and very specifically, very quantitatively, what the field of that wire looks like. So we're going to want to be specific about the direction of the field and specific about the magnitude, the size of the field. So this slide here is about the direction of the field. And as I mentioned, the field lines form loops, concentric circles around a current-carrying straight wire. And the question is really, in which direction does the field circle around a current-carrying straight wire? Does it circle clockwise? Does it circle counterclockwise? There's two possibilities. The answer comes from a right-hand rule, another right-hand rule, you'd be pleased to know. So the right-hand rule for the direction of the field of a current-carrying wire is to get your right hand. You're going to point your thumb in the direction of the current flow. So in this sketch here, the current flow is from the bottom of the screen to the top of the screen. So I'm pointing my thumb upwards. Your fingers of your right hand will naturally curl in the direction of the magnetic field that's produced by that current. So if you look at my fingers, they're curling into the screen on the right of the wire, over here on the right. And they would curl out of the screen on the left of the wire. And so the field, according to the right-hand rule, and it's shown here, the loops of field are circles around the wire where they, in the case of a current that's heading up, they will enter the screen on the right and exit the screen on the left and circle in this sense around the wire. And that's the right-hand rule for a current-carrying wire. What about the magnitude of the field? The wire's influence, magnetic influence, gets weaker the further you are from the wire. So the wire's magnetic field falls off, decreases as you get further from the wire. This equation on this slide tells you exactly, precisely, how the magnetic field falls off from a current-carrying wire and how it depends on the current in the current-carrying wire. So this equation upstairs here, this is an equation for the magnitude of this field. And the magnitude of the field we see depends on the current, so that's the I in this equation. Depends on the radial distance from the wire, that's the R in this equation. And you can see here that if you have a larger current, well, you're going to get a larger magnetic field. because the magnetic field is proportional to the current, and that would make some sense. If you have a small current, that will create a smaller magnetic field because the magnetic field is in proportion to that small current. So that's one feature of this equation. Then the second feature here is that the further you are from the current carrying wire, proportionally, the strength of the field goes down. So if you double the distance from the current carrying wire, then you're going to halve the magnetic field. If you triple the distance, you're going to have just 1/3 of the strength of the magnetic field. So the magnetic field strength or size and magnitude is in proportion to the inverse of the distance, the radial distance from the wire. And so that's in the equation here. This factor here, mu naught over 2 pi, this again, this mu naught is a constant characterizing the strength of magnetism, like we had constants that characterize the strength of electricity, like we had constants that characterize the strength of gravity. They were the Coulomb constant K, they were the gravitational constant big G, and this is another constant, mu naught, that characterizes the strength of magnetism. And its value, I've written it down here, is 4 pi times 10 to the minus 7. And here are the units, Teslas, meters over amps. If you think about these units here, Teslas, meters over amps for mu naught, when you multiply it by a current, you'll cancel out the amps. When you divide it by a distance, you'll cancel out the meters. That gives you a magnetic field in Teslas. So it has to be those units. Okay, let me show you a demonstration of the magnetic field. So you can see it in the overhead here, or you can see it in the demonstration here. This is a wire, and I've got the wires connected, or a circuit is made to a power supply down here. Better switch it on. I've got a switch, and it's actually one of these reversible switches. And so if I push the switch towards you, I can send the current in one direction, say up the wire. If I pull the switch towards me, I can send the current in the opposite direction, down the wire. Now what you can see in the camera here is 4 compasses that are laid out around the wire. And if you look at the compasses right now, they're all pointing in the same direction. They're all pointing, if I stand here, they're all pointing kind of towards me. And they're all pointing towards me because towards me is north. And so they're pointing in that direction because they're measuring the Earth's magnetic field right now. That's because the wire, the circuit, is not switched on right now. The switch is open. But if we close the switch, and so this is, when we do this, think of this is exactly what Hans Ørsted first saw. This is exactly how he first discovered that currents make magnetic fields. So I'm going to close the switch, and look at the response of the compass needles. So suddenly, through that empty space between the wire and the compass needles, there's some influence. The current's having some influence, is having a magnetic influence. And now if you look at the compass needles, look at, if you can see the white tips here, at this end, upstairs here, and on the far right of the top compass needle, they follow a circular path around the wire. They're mapping out lines of concentric lines of magnetic field that now exist around the wire. And so we're seeing the magnetic influence of the wire. If I open the switch, and it takes a little while here, the compass needles will go back to pointing towards north. Now they're just bathed in the Earth's magnetic field. So again, now that if you look at the white ends of these compass needles, here, 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 and upstairs here, they're all pointing kind of over to this corner of the room, and this is north. And then if I flip the switch in the other direction, again, suddenly they're influenced by the presence of the current in the wire that's passing between them, and now they're forming kind of circles around the wire, And you might notice now that the white ends of the compass needles are on the opposite side. So now they're circling in the opposite direction around the wire. We've reversed the magnetic field that's surrounding the wire because we've reversed the current that's flowing through the wire. Okay. Here's a little question in which we can use an understanding now of a current-carrying straight wire. In this question, we're told that we've got two current-carrying straight wires. One of them is carrying a current along the x-axis. One's carrying a current along the y-axis. One of them along the x-axis is 7 amps. The other one along the y-axis is 6 amps. And based on that, we're going to calculate the magnetic field at some particular point in this xy plane that has the coordinates, we're told, 4 meters, 3 meters. X is 4 meters, and y is 3 meters. And so let's go ahead and solve this problem. I'm going to do that on the, whatever this thing is called that I can never remember. I'm going to solve it here. So I started it already, and I've drawn, the important thing is I've drawn a sketch. I've drawn a sketch where I've indicated the two currents. The horizontal one was 7 amps. I called it I1. The vertical one was 6 amps. I called it I2. And then we want the field at this point here. So that's our task, is to find that field. Now, that field at that point is a superposition of two fields. We've got two straight wires. And so the first idea here is that that field's going to be a superposition. I'll call the total field B. It's going to be a superposition of B1 and B2. So these two vector fields will add together to make the total field. We met this sort of thing with electrical fields, where a couple of electrical fields would add together to make a total electrical field. Now, that means we've got to worry about adding together vectors. But here, it's not too complicated. Let me write down the way I added them, and then I'll explain it. So the first thing I did was to figure out what the direction at that point the field due to I1 is in, and what the direction at that point the field due to I2 is in. And I used the right-hand rule. So let's do the horizontal current. I'm going to point my thumb in the direction of the horizontal current. So I1's going over towards the right-hand wall. My fingers curl around my thumb, and in that region above the wire, where that point is, they're coming out of the screen. So I1 is out of the screen, and I'm going to call that the positive direction. Now let's do I2. I2 is heading upwards, so I'm going to point my thumb towards the roof. My fingers are going to curl in the direction of the magnetic field around I2. On the right-hand side of I2, they're curling into the screen. So B2, the magnetic field B2 of I2 is into the screen. The magnetic field of I1 was out of the screen. And I got those two facts just from this right-hand rule thinking. And so that's what I've written down here. I'm going to call out the positive direction. That's the direction that the field of the horizontal wire is at this point. And then that means that B2 will be in the negative direction. It's in the opposite direction. So the plus means out, the minus sign means in here. So that's handling the fact that these are vectors. And now all I've got to do is fill in the magnitudes of these two fields. Well, the magnitudes of these two fields is given by that field law. that we just wrote down. And there's a common factor for both fields, right? It's that constant involving mu naught. And then that multiplies, if you remember the field equation, it multiplies the ratio of the current to the distance, the radial distance from the current. And so we've got an I1 over R1 and an I2 over R2. Let me be clear what R1 and R2 is. This is R1. It's the radial distance from the horizontal wire. So this is going to be, it's important, this is 3 meters, not 4 meters, this is 3 meters, because the radial distance is in the y direction. This is R2. Again, it's the radial distance from the vertical wire, the second wire, and this is 4 meters. That's the horizontal distance to this field point. And so those are the two distances. At this point, I know, right, the two currents, 6 and 7 amps. I know the two distances, 4 and 3 meters. All I got to do is plug in those numbers. I'm not going to write them all out. But if I plug them in, I got 0.17 plus 0.17 microteslas. That's a 10 to the minus 6 of a Tesla. So it's a tiny magnetic field. It's a tiny magnetic field because the characteristic strength, mu naught, that's a tiny number. It's positive because the field of the horizontal wire that's coming out, that's bigger than the field of the vertical wire that was heading in. That field was bigger, the horizontal wire, both because the current was a bit larger and because we were closer to that wire. The other wire, the vertical wire, has a bit smaller current and it's a bit further away, so that made that a smaller field. Okay, so that's an example. Feeling disorientated right now. What am I doing? Okay, I want to move on to a related topic, a closely related topic, and that's the force between two parallel current-carrying wires. So now I've said that a single current-carrying wire makes a surrounding magnetic field. If you place a second current-carrying wire in that magnetic field, you'd expect a magnetic force. And so we're going to calculate that magnetic force. So in a sense, this is another example, right, of the field law that we've just met. We're going to calculate how that field law creates a force on a second wire. So let's go ahead and do that. So here's the situation. I've got two current-carrying wires. This one upstairs here, that's carrying a current I1. This one downstairs is carrying a current I2. And they're separated by some distance. And we want to find the force, for example, that I1 exerts on I2. What is the force that the upper wire is exerting on the lower wire, or vice versa? What is the force of the lower wire on the upper wire? So how are we going to do that? We're going to do it kind of in two steps. We're going to combine something from this class and last class. This class, we've just met the field of a current-carrying straight wire, so we're going to use that. Last class, we met the force on a current-carrying straight wire in a field, so we're going to use that. We're going to put two things together to create the force, to figure the force between two current-carrying wires, which is a very famous example in magnetism. It's a very basic example in magnetism, to be able to say what the force between a pair of current-carrying wires is. So as we do this, we're going to use this equation here. So this is the equation for the magnetic field surrounding a current-carrying straight wire. We just met this one. And we're going to use this equation here. Remember, this is the field equation. This tells us the force that acts on a current-carrying wire in a magnetic field. So this was the field equation. So these two equations, we're going to put them together to find the magnitude, the size of the force between the two wires. We're also going to use right-hand rules for the fields and the forces to find the directions of the forces between the two wires. So again, think of this as an example, an illustration of our magnetic field law from this class and our magnetic force law field equation from last class. We're going to do it in two steps. So the first thing I'm going to do is, what is the first thing? Find the direction of the force. What's the direction of the force? So the way to find the direction of the force is that we're going to pick one wire, and we're going to find the field at the other wire due to that wire. And then we're going to imagine that other wire in that field and figure out what force it experiences. So in this particular case, I started with wire number 2. So this wire here is creating a field that's given by the right-hand rule, and it's going to create a field at the location of the upper wire, wire number 1. So the field due to I2, that current I2 is going towards the right. So the field is going to be given by my fingers, which curl out of the screen above the wire. They would curl into the screen below the wire. Above the wire is where the other wire is located. So the field B2 due to I2 is coming out of the screen. That's what I'm trying to show here in the green arrow. So that's one right-hand rule. Then we can use the other right-hand rule. The other right-hand rule is for the direction of the force on a current in a magnetic field. So in the other right-hand rule, what do? You point the palm of your hand in the direction of the current. So my palm is going towards the right because the current in I1 is going towards the right. And I'm going to curl my fingers in the direction of the magnetic field. Well, to do that, I've actually got to flip my hand over. I'm keeping my palm pointing towards the right because that's the direction of the current. And I'm going to curl my fingers in the direction of the field, which at the location of wire number 1 is out of the screen. My thumb then points in the direction of the force. The force is downwards. So wire 1 is being attracted. We've just discovered this. A huge discovery when this happened. We were just a bit late. Huge discovery. Wire 1 is being attracted to wire number 2. And if we did the same thing, if we figured out the field of wire number 1, the upper one, at the location of wire number 2, and then the force on wire number 2 due to that field, we discovered that wire number 2 is also being attracted. So these two wires are being attracted to one another. They're being pulled to one another. And that's a basic feature. Parallel wires, parallel current-carrying wires attract each other. If the currents had been flowing in the opposite directions, opposite currents actually repel one another. So this is another law that sounds a bit like charges repel, unlike charges attract. Like poles repel, unlike poles attract. This is that like currents, they don't repel. Like currents actually attract one another. And unlike currents, so opposite currents, they actually repel one another. So think of this as a third one of those laws about about charges attracting or repelling, about poles attracting or repelling. This is one about parallel or opposite currents attracting and repelling, but it's the opposite way round. It's the like currents that attract each other. It's the opposite currents that repel each other. So that was a huge discovery. Now we want the size of the force. Well, all we got to do is follow that same recipe that we did on the last slide. We're going to find the size of the field due to current 2 at the location of current 1. So we'll find that field using the field, the equation for the field of a straight current carrying wire And then we'll use the law that relates to force on a current to the field at the location of the current to find the force. And so that's what I'm going to do here. This is the equation for the field due to current number 2, I2, at the location of current number 1. So it's a distance d away. This is the equation for the force on current number 1 due to the field, B2, at the location of that current. So this is the field equation, and this is the equation from today's class. If I simply plug the equation from today's class into the equation from the previous class, so plug the expression for B2 into this expression for the force on wire number 1, I get this equation here. And this equation is the equation for the force between two current-carrying wires. So let me say a few words about that equation. So that force depends on the currents in both wires. So if you increase the current in wire number 2, that would make a bigger field. If you increase the current in wire number 1, it would feel that field more. So I1, I2 is important. It's the product of the two currents that's going to determine the force. It's like the product of charges determines the force in Coulomb's law. So that's rather similar to Coulomb's law. The force gets weaker the greater the separation between the two wires. So if you were, this is the separation D here, and it's in the denominator. So if we increase the separation, we're going to get a smaller force. If we double the separation, we're going to get half the force. Triple the separation, we're going to get a third of the force. That's because if we double or triple the separation, then the upper wire is in 1/2 or 1/3 of the field of the lower wire. And so the force between the two wires is going to fall off with distance. Now, interestingly, it's falling off with the inverse of the distance. It's not like Coulomb's law, where that fell off as the square of the distance. So that's something to be careful of. This falls off more slowly for these long, straight current-carrying wires than Coulomb's law between two-point charges. So it is different in that respect. There's one other difference. This is actually not an equation for the force on the wires. This equation here is for the force per unit length. So this is an equation for F over L. This is the force per unit length on the wires. So this is the force per meter on each wire. If you actually wanted the force in newtons on a particular wire, you'd have to multiply by the length of the wire. So the equation we just figured is for the force per unit length. That's another difference from Coulomb's law, where it's just the force between a pair of charges. This is the force per unit length between a pair of currents in parallel or opposite wires. Okay. There's another example in there. I wanted to post that example as an illustration problem. I'll put it on Canvas. But I wanted to move on now to I wanted to show you a demonstration. Okay, on the screen, you can see if I can find the pointer, a red wire and a black wire. So two wires. Here's the black one, here's the red one. And so these are parallel wires. They're the wires inside this box here. I'm going to pass a current through these wires. Now, with a reversible switch, if you can see this, I can pass the currents such that they're in the same direction, or I can pass the currents such that they're in opposite direction. If they're in the same direction, we're going to expect attraction between the two currents. In their opposite direction, we'd expect repulsion. And so let's try attraction first. I'm going to press this switch, and that's going to send the currents in the same direction. It's not on yet. Okay, so we're not seeing any deflection of the wires yet. And there's some statement in here because of fire that we started last time that I can't, so you've got to watch, because I can only press the switch for a few seconds before smoke starts to come out of these wires, because we're going to pass to get this attraction. Remember we calculated the field of a current carrying wire. It's really rather tiny. You've got to put a lot of current through these wires to create a measurable, a sizable force. So I'm going to flip the switch and watch the wires. And so they pull together. There was a strong attractive force between those two wires. That's the magnetic influence of one wire on the other wire. That's governed by, that force we just saw there is governed by that law for the force per unit length being the product of the currents and the inverse of the distance between the two currents. So that's an example of that law. I'm going to flip this switch and make the currents go in the opposite direction. So if we're right, if we had derived this, we said that they would repel if the currents are going in the opposite direction. So let's watch this case. And nothing happens. Try again. Yeah, here's the repulsion. Of course, they swing out of the way and then they start to fall back. But that's the repulsion case. Maybe not as dramatic, I thought, as the attraction case. But it's still amazing to see this influence, this magnetic influence through empty space due to this kind of ethereal or ghostly magnetic field between these two current-carrying wires. Okay. I wanted to talk about the field of a single current-carrying loop. So that's the case over here on the right-hand side. Imagine this is just one loop of wire, and somehow we've got a current that's flowing around this loop of wire. And I'm going to compare that field to the field of something that we've met before, sketched before. It's the field of a bar magnet. Over here is a bar magnet. Upstairs is a north pole, and downstairs is a south pole. In green, in both cases, I've sketched for you, because we know how to read these sketches and understand these sketches, what the magnetic field of the bar magnet that we met before, and what the magnetic field of the current-carrying loop that is new, what they look like. And there's remarkable similarities between these two fields. So if you look at the two fields, the field lines come out of the North Pole on the bar magnet, and they're coming out of the top of this current-carrying loop. The field lines loop around and head into the bottom of the bar magnet at the South Pole. And they also loop around from the top of the current loop to the bottom of the current loop. And so we actually call this the North Pole of the current loop, and this the South Pole of the current loop. Also, look, the field tends to be strong near the current loop, and the field is strong near the magnet, and the field falls off far from the magnet, and the field falls off far from the current loop. So you can see that from how closely, or whatever the opposite of closely is, far apart, the field lines are spread out. And so this is remarkable, really, that this single current carrying loop is creating a magnetic field that looks just like a bar magnet. You would probably never have guessed that, because you would say, well, look, the current carrying loop in a little circle is completely different from a bar magnet. But actually, we understand now that current carrying loop and a bar magnet are very similar in terms of currents. Inside the bar magnet, although you can't see them like you can for the current loop, there's currents circling around the walls of the bar magnet. And the bar magnet itself is just like a current loop that's creating a north pole and a south pole, just like the single current loop is creating a north pole and a south pole with the field lines coming out, the field lines going in. Okay, so that's what the field looks like. It's a complicated field to write an equation for, right? Because its direction is changing everywhere, its size is changing everywhere. But for a simple current loop, there is a simple equation for the field at the very center of the loop. And so that's an equation that we can discuss. That's the equation on this side. And also the direction of the field at the center of a current loop has a simple rule for that direction. And so let's discuss these two things. So here's our current loop over here on the left-hand side. In this case, the current is heading around in this direction. So it's coming out of the screen on the left. It's going into the screen on the right. The radius, the dimension of the current loop, is given this symbol A. So A is the radius in meters of the current loop. And here's the magnetic field. Here's a sketch of the magnetic field at the center. This is the magnetic field vector at the center. And it's this vector's direction, this vector's size, that we want to quantitatively describe. So first of all, the direction of that field. That's also, you'd be really pleased to know, another right-hand rule. Right, we just had a right-hand rule where we pointed our thumb in the direction of the current and the fingers curled in the direction of the field. Now we're going to reverse that. Now we're going to curl our fingers in the direction of the current, and our thumb is going to point in the direction of the field. So if you look at the direction of the currents coming out of the screen on the left and going into the screen on the right, so look like this. My thumb then points in the direction of the field. The field is heading straight upwards. And so that field is related to that current. The direction of that field is related to the direction of that current via this right-hand rule. If I were to change the direction of the field such that it would come out of the screen on the right and go into the screen on the left, then I'd correspondingly change the direction of the magnetic field. It would be downwards now. And so it's a right-hand rule, another right-hand rule that gives us the direction here. The size of this field, here's the equation for the size of the field. Now, again, let me stress, because this is important, this is just the size of the field at this very special point, at the center of the current loop. It's given by this little equation here. In the numerator is the current in the current loop. Of course, that's not surprising, right? If there was no current, there'd be no field. The bigger you make the current, the bigger you make the field. So that makes sense. In the denominator is the size of the loop. So the bigger the loop, the further away the current is from the center, then the weaker the magnetic field. That makes sense too. We kind of saw that effect with the straight wire. The further we were away from the straight wire, the smaller the magnetic field of the current in the straight wire. Same thing here. The further away, the greater the radius of the current carrying loop, then the smaller the magnetic field. Okay. Oh, I wanted to show you a demonstration. So we just said that a current-carrying loop and a bar magnet have very similar magnetic fields. They both have north poles. They both have south poles. And so actually, you know, before we looked at the attraction and repulsion of the poles of a bar magnet, we should be able to see the same kinds of attraction and repulsions between a bar magnet and a current loop. Well, here is a little arrangement where I've got a bar magnet. Here's the south pole. And I got a current loop. Now, right now, there's no current flowing in the current loop. But if I made the current go in such a way that the south pole would be below the current loop, then I'd get repulsion. If I made the current go in such a direction that the north pole is below the current loop, then I would get attraction between the bar magnet and the current loop. And so let's see if we can see that. So I've got power supply again. I'll turn that on. And then I've got the famous reversible switch. So if I push this switch towards you, the current will go in one direction. If I pull the switch towards me, the current will go in the opposite direction. So this is how I can, with a switch now, change this arrangement from having the North Pole at the bottom to the North Pole at the top. South Pole at the bottom to the South Pole at the top. I'm going to push the switch towards you. I know no idea which way around this will go. And look, I'm getting a traction. So that means that the North Pole must be below this current loop. The South Pole's upstairs here. And that current loop is being pulled down by the remarkable attraction between a bar magnet and a current loop. So let's turn that off. Let's let it settle. It's really, really hard to get this to stabilize. Oh, I did it. How did that happen? I've never done that before. Okay, but that's made me forget about what I was going to do. I was going to change the direction of the current. So I'm going to now pull the switch away from you towards me. And we're going to expect to see repulsion because I've reversed the poles on the current loop. So let's try that. And it's not working. It is working. It's going. It's barely working. Let's see if I can get it. Up you go. I'm going to treat it like a kid's swing. And every time it goes up, I'm going to give it another little push up. So here we go. And it's falling down and it's going up. I'm going to give it another current push. And so I hope I'm demonstrating that whenever I close the switch, I get a repulsion between these two guys. Again, it's open now, and then I'll give it a push up. And I'll do it one more time because it's so much fun. Here we go. Okay. I wanted to solve a problem involving current loops. So here's the problem. In this problem, we've got two current loops. There's a smaller one, that's loop number 2. Radius is 9 centimeters, and the current's going counterclockwise. Then there's a bigger one. Radius is 12 centimeters, and that current's going clockwise. And we've got to find the field at the center of these two concentric loops. So this is a problem, again, like an earlier problem, where we've now got two current loops, not two straight wires, but we've got to superimpose the two fields of the two current loops. So we've got to take account of the directions of the fields of the two current loops. And then we've got to worry also about the sizes to get the magnitude of the resulting magnetic field. So I'm going to also solve this one on the thing I don't know what to call. Okay, so here's my attempt at starting this problem with a sketch. And if you remember, the outer loop had radius 12 centimeters. I called that R1, and it's got the higher current. It's 5 amps. The inner loop had a radius 9 centimeters. I've called that loop 2, and its current was 3 amps, smaller current. They're concentric, so that means that it's centered on the same point, and that's where we're going to find the magnetic field. So the basic idea, again, right, is that the magnetic field at that center, B, is the superposition of the two magnetic fields of the two current loops. So it's going to be B1 plus B2. Where here I'm writing B and B1 and B2 as vectors because they are vector fields. They have sizes, they have directions. In adding them up, we're going to have to deal with the directions and deal with the sizes. I'm going to deal with the sizes first. No, I'm not. I'm going to deal with the directions first, and then we'll deal with the sizes second. So let me write down how to deal with the directions. here's how I've dealt with the directions, that the resulting magnetic field is going to be minus B1 plus B2. My reasoning here was, look, B1 is clockwise. So B1, if I want to curl my fingers in the direction of B1, that's the wrong way. It's this way. This is my right hand. And I'm curling my fingers in the direction that current I1 is flowing. So at the bottom, look at the bottom of the loop, is flowing from the right to the left. So that's the way my fingers are going. My thumb's pointing in towards the screen. I'm going to call that the negative direction, in towards the screen. The other current, so that's I2 in the smaller loop, that is flowing, that's flowing this direction. Why am I having trouble with this? Because I'm human, maybe. My hand is now in the direction of the current flowing through the smaller loop. So at the bottom of the smaller loop, it's from the left to the right of the room. And my thumb is pointing out of the screen. This is the opposite direction, because the currents are in the opposite direction. So we've used the right-hand rule. We figured out that at the center of the loop, the field due to the smaller loop is out. The field due to the larger loop is into the screen. I'm calling out of the screen positive direction, so it's plus B2. I'm calling into the screen the negative direction. It's minus B1. So that's handling of the directions. Now we've just got to handle the sizes of these two fields. That's with that field equation, field law that we just met for the field at the center of the current loop. There's a common factor again. It was mu naught over 2. That's that constant that characterizes the strength of magnetic forces and magnetic fields. And then it's multiplied by the ratios of the current to the radius of the loop. So there's an I1 over R1, and then there's a I2 over R2. And so that's the equation. And if you look at that equation, all the numbers on the right-hand side, I know the two currents, I know the two radii. All I got to do is plug in the numbers and the constant mu naught, and I won't write all that out. But if you do plug in those numbers, I got minus 5.2 microtesla. So again, it's a tiny, let's comment on that. Microtesla, that's a tiny magnetic field. It's a tiny magnetic field because of mu naught is a tiny number. Everyday currents, amps or fractions of an amps, produce small magnetic fields. We needed really big currents, kilo amps, to produce big magnetic fields, big magnetic forces. So that's why it's a small number. The minus sign is saying that the resulting field is inwards. It's into the screen. It's into the overhead. That's the direction that the field B1 was in. It's opposite the direction of the field B2. That's because the field B1 is actually bigger. The field B2 is smaller. You see, B1 had a much bigger current that more than compensated the fact that its radius was bigger. So there was kind of a battle going on in this problem. The smaller loop was going to create a bigger field because it has a smaller radius, but the outer loop was going to create a bigger field because it had a bigger current. The ratio of the currents was bigger than the ratio of the radii, and so the big loop, the larger loop with the larger current won out. And it's and although they largely cancel one another out, the field B1 was bigger than the field B2, and so it did win the whatever it is I'm talking about, the race. I don't know. Okay. I'm completely disorientated. Last topic, I want to talk about the magnetic field of a solenoid. And so I've got to explain a little bit what a solenoid is, and then we'll talk about its magnetic field. Here's a picture of a solenoid. So a solenoid is really just a chain of single current loops. So we just talked about the field of a single current loop. We talked about the direction of that field. We talked about the magnitude at the center of the current loop. A solenoid is just a whole bunch of those current loops chained together. And so that's what's shown in this slide here. You know, here's one loop. Here's the next loop. And here's the next loop. And so on and so forth. I won't go on forever, obviously. So it's a whole chain of current loops. And each one of those loops will create a magnetic field, of course, and the magnetic fields of all of those loops will superimpose together. Now, that sounds like a very complicated problem. You know, we already saw that the field of a single current loop was kind of complicated, although there was an equation for it at the center. But imagining superimposing all the fields of all these current loops looks very complicated. But actually, this is an amazing thing. It turns out to be really, really simple. This arrangement produces a uniform magnetic field everywhere inside the volume, the body of this thing we call the solenoid. So everywhere inside here, the walls of the solenoid, is a constant size, constant magnitude magnetic field. Everywhere inside there is a magnetic field that's along the direction of the solenoid, always in the same direction. So it's a very famous, very important magnetic field. It's how we build, how we create, construct a uniform magnetic field. We do that with this thing we call a solenoid, which is just a chain of loops of current-carrying wire. I don't know if this helps. So this is a slice, especially it doesn't help if you're at the back, but this is a slice through a solenoid. So here are the loops of wire of the solenoid. And here and here in yellow and green, this is where the current will be coming out and then heading back into the screen. And so it comes out, goes back in, comes out, goes back in, and so on and so forth. This in red, the extra ingredient in red, is what the field looks like. The field inside the walls of the solenoid is a uniform magnetic field that streams along the length of the solenoid. So it's how we make this uniform field. Okay. This sketch here is meant to make you believe me. Believe me that by combining many loops of current-carrying wire, we can create a uniform magnetic field. What you're seeing on the left-hand side as you move to the right-hand side, you've got to imagine this is just you constructing a solenoid with closely packed current loops by bringing together many individual loops. So here are a handful of loops, 5 of them, that we've collected together. We're pushing them together. And as you push them together, the individual fields of each loop coalesce, combine, superimpose, whatever your favorite word is, to create this field here. You see the field lines kind of collect between the coils, between the loops, and are creating a roughly uniform magnetic field. If you pack these loops very densely, and so that's what you're seeing here on the right, each one of these is a loop of wire. Here's the current coming out, here's the current going back in, coming out, going back in, coming out, going back in. You ultimately produce this region of uniform magnetic field. Upstairs here, this is the equation. This is an equation that describes that magnetic field. And so this is an important equation for a solenoid. The magnetic field inside a solenoid is, firstly, it's in proportion to the current that's flowing in the windings of the solenoid. So that's probably obvious, right? All of our magnetic fields, for the single loop, for the straight wire, they're all proportional to the current. And so it's no different for the solenoid. The field inside the solenoid is proportional to the current. The second thing that the field inside the solenoid is proportional to is what we call the number of turns per unit length. So the number of turns per unit length in this overhead here is given the symbol little n. It's the ratio of the number of turns of the solenoid, the entire number of turns of the solenoid, so that's the uppercase N, divided by the length of the solenoid, how long the solenoid is. That's the uppercase L. So uppercase N, the number of turns of the solenoid, divided by uppercase L, the length of the solenoid. So it might be, uppercase N might be 1,000 turns. The length of the solenoid might be 1 meter. If we divide one by the other, we get the little n, which is the number of turns per unit length. And that field inside the solenoid is it's not in proportion to the number of turns. It's not in proportion in some way to the length of the solenoid. What counts is the number of turns per unit length. So the greater the number of turns per unit length, the greater little n, the bigger the field. The smaller the number of turns per unit length, the smaller the field. What that really means is the more tightly you wind the solenoid, the more turns you put per centimeter or per meter or per millimeter, the greater the magnetic field. The less tightly you wind the solenoid, the less turns per meter or centimeter or millimeter, then the smaller the magnetic field. And so I would tend to look at this equation here, this part of the equation. This is the field inside the solenoid, mu naught I n, mu naught I lowercase n. It's the field inside this ideal solenoid. It's the approximate field inside this real solenoid here. And it's in proportion to the magnetic permeativity, that's the mu naught, that's the constant describing magnetism, multiplied simply by these two numbers, the current and the number of turns per unit length. And so if you want a certain size uniform magnetic field, you can just adjust the current or just adjust the number of turns per unit length to create that particular size magnetic field that you want to construct, that you want to build. Okay, got a quiz question. Oh, I didn't actually publish it, did I? No, I am. So this question asks you to compare two solenoids that we've called A and B, A on the left, B on the right. We're told that the solenoids have the same lengths. We're told that the solenoids have the same number of turns. That's the number of loops. We call turns the number of loops. And they have the same currents that are flowing in them. But they do differ. They differ in their radii. So obviously from the picture, the one on the left has a smaller radius, the one on the right has a larger radius, and the question is, how do the magnetic fields in the two solenoids compare? Is A larger? You're closer to the wires. Is B larger? There's more wire carrying current. Or are they the same? So I'll give you a minute or two to think about that. Okay, so let's answer this question. Um, the the two magnetic fields inside the bodies of these two solenoids are the same. Right? The magnetic field inside a solenoid is given by B, the magnetic field, equals mu naught, the magnetic permittivity, times the product of the current and the number of turns per unit length. So I times lowercase n. Both these solenoids have the same currents flowing in them, we're told that, and they also have the same number of turns per unit length. They had the same lengths, and they had the same total number of turns, so that's the same uppercase N over uppercase L. It's the same number of turns per unit length. So that determines the field. They both have the same fields. The only difference between the big radius, small radius pair of solenoids is that the field inside the big radius solenoid is the same size, but it's spread over a bigger volume, because inside that solenoid is a bigger volume. The field for the smaller radius solenoid, that's spread out over a smaller volume, because it's a smaller radius solenoid. So there is a difference in the volume that the fields occupy, but there's no difference if they carry the same currents and have the same number of turns per unit length in the strengths of the fields. Okay. So here's an example question that involves that equation for the magnetic field of a solenoid. It says we've got a 10 centimeter diameter, 75 centimeter long, I missed out a word, solenoid, is built from 1 millimeter diameter copper wire, wound in one layer of touching turns. And we've got to figure out what current is needed to create a magnetic field inside the solenoid that's 8 millitesla. So let me just, first of all, let's make sure we understand, because this sentence was so screwed up, what I'm talking about here. This solenoid has a 10 centimeter diameter, so it's like this. This solenoid is 75 centimeters long, so it's kind of like this. I've made this solenoid by taking a wire, 1 millimeter diameter, and wrapping it around the walls of the solenoid, where each turn I put the wire touching adjacent to the previous turn. So I make a new loop, a fresh loop. The new wire is going to touch the previous wire. The next loop, fresh loop, the new wire is touching the previous wire. That's how I'm packing the wires as I build the solenoid, construct the solenoid out of many turns. So based on that information, we're not calculating the field here. We're calculating the current to make a field here, which is, if you're building a magnet, that's typically what you want to do. You want a certain magnetic field. Well, you've got to figure out the current that you need to make that magnetic field. Okay, so let's solve that. Again, I'll solve it on this thing that I don't know the name of. Here we are. So I made a sketch over there on the right-hand side. No, on the left-hand side. And I've annotated the sketch with information that I know and information that I want. And I also did a couple of little extra calculations down here. Okay, so let me, here's the solenoid. This is typically how we sketch a solenoid. There's a magnetic field that's created by this solenoid. It's 8 millitesla, and it's created by a current that's flowing in the solenoid, and that's what we want to figure out. I knew some geometrical information about the solenoid. I knew the diameter of the wire that I wrapped around the walls of the solenoid in one single layer is 1 millimeter, or 10 to the minus 3 meters. And I know the length of the solenoid is 75 centimeters or 0.75 meters. I thought, well, look, I'm going to want to know the number of turns per unit length of the solenoid, because that's the key thing about any solenoid. To figure out the number of turns per unit length of the solenoid, here I've actually got to calculate the number of turns of the solenoid, because we're not directly told that. And so my thought process was, if I have one, was to calculate uppercase N, the number of turns, because it was explained to me how I made the solenoid. And then once I've got uppercase N, I'm going to calculate lowercase n, which is going to be the number of turns per unit length of this solenoid, which is the key characteristic of the solenoid. So look, the number of turns per unit length, the N, uppercase N, the total number of turns is the length of the solenoid, that's 0.75 meters, divided by the width of one loop of solenoid. So when I do one turn of the solenoid, that's 1 millimeter wide, because just one wire's width wide. That's hard to say. One wire's diameter wide. And so if I divide the length of the solenoid by the diameter of the wire, that's the number of turns. So 750 turns as I build this solenoid. The number of turns per unit length of the solenoid is that 750 turns divided by the 75 centimeters. So that's 1,000 turns. I should have put per meter here. There's a dimension here. This is 1,000 turns per meter. Well, I mean, I can still put that there, can't I? I'm thinking this is an overhead. Okay, so anyway, that was my starting point. Now I said to myself, I want to calculate the current that creates a particular magnetic field. So I'm going to go to my master equation for the solenoid, that the field is mu naught times the number of turns per unit length times the current. So B equals mu naught Ni. I want I. And so I just got to divide through by mu naught and N. So it's going to be B over mu naught times N. And then I can fill in these numbers. I won't fill in all the numbers. I got 6.3 amps. So I filled in 8 times 10 to the minus 3 Teslas. So that's a small number. But I filled in mu naught, which is 4 pi times 10 to the minus 7 Teslas meters over amps. So it's a much, much smaller number. I filled in N, which is a big number of 1,000. And I end up with this number of amps. And so that was my current.